Good morning and welcome to our lesson today. We are still on waves and we started on properties of waves. We went as far as reflection and we found out that the nature of the reflector is of importance when it comes to the behavior of the wavefronts after reflection. Today we want to go further and talk about refraction. And refraction basically is the bending. It's the bending of wave fronts when they travel from one medium to another. From one medium to another, we expect that there are some things or some characteristics that are going to change about our wave. Now, for example, let us assume we had some plane waves, whose wavefronts are actually perpendicular to a boundary, and we want them to move from deep water to shallow waters. Now we have a boundary here that is separating deep waters from shallow waters. Now we expect that our wavefronts are not just going to pass on like that. Rather, there is going to be some change in characteristics of those waves. For example, now we will realize, let us take this to be our boundary. Let us take that to be our boundary. We expect that the spacing between our wavefronts is going to be compromised. And that is because as we move from the deep to the shallow waters, we are going to have a change in speed of the wavefronts. That way, we are going to expect that now the spacing which represents our wavelength is going to also be compromised. So basically here, spacing between wavefronts reduces. The spacing between wavefronts actually reduces, and that one translates to reduction in speed. Our wavefronts are going to reduce their speed, and that one translates to the difference between the wavelengths. Now, when we were tackling the other lesson, we looked at a relationship where we were comparing the relationship that exists between the speed, the wavelength, and the frequency. And we said that frequency is always constant. Always constant. Now, if we should say that speed is actually a product of wavelength and frequency, and again, we claim that our speed has reduced. Now, it means that on the right-hand side, we ought to have another factor that will reduce proportionally to the reduction in speed. And now that we are claiming that our frequency will always be constant, then the factor to consider should be our wavelength. It actually reduces also, so that now we can strike a balance between the two sides of our equation. Therefore, what we are saying is that when we are changing media of wave travel, you expect some bending. For example, when we look at light, as it moves from one medium to the other, we claim that it actually bends. For example, if you put a ruler in a glass of water, it will actually look as if it's broken. But in the real sense, we are talking about that bending as we move between different media. Now we could consider that we have just looked at is where wavefronts are parallel to the boundary. The case we have just discussed is when our wavefronts are parallel to our boundary, so that when they bend, what is evident is actually the reduction in wavelength, which we have attributed to the reduction in speed and subsequently the wavelength according to the relationship speed as a product of wavelength and frequency, and bearing in mind that the frequency of our waves will always be constant. Now, I want us to consider another case where wavefronts meet the boundary, where the wavefronts meet the boundary at an angle, where the wavelength meets the boundary at an angle. Now here, again, we are going to experience the change in speed, but then look at this. We have the wavefronts. We have our wavefronts, which we are claiming that the direction of motion of the wave is in that direction. Then we could have our boundary at an angle to the wavefronts. That is our boundary at an angle to the wavefronts. Now, we expect that the waves will be refracted in such a way that, again, the speed will also reduce, so that now we have the wavefronts being close to each other. This is direction of incident wave, direction of incident waves, and this one here again is the direction when they bend. This will be the direction of refracted waves, refracted direction of refracted waves. Now, there is this angle here, this one, and this one. Angle I is what we call the angle of incidence. Angle of incidence. And number 2, the angle R is what we call the angle of refraction. And now there is that relationship that exists. Much as we have seen reduction in wavelength, of course, from the relationship that we have just been discussing, we can explain why we have wavelength 1 being being greater than wavelength 2 is because of that reduction in speed as we cross from the medium 1 to medium 2. We have that reduction in speed, and which will translate to reduction in the wavelengths. However, we have said that we have an angle I, which we are claiming to be the angle of incidence. We have tried to come up with a normal. This is the normal, so that we can clearly see the angle I as well as angle R. Now, the angle of incidence and angle of diffraction will be related in a relationship that we call the refractive index, which is equal to sine I over sine R. So this relationship is what is going to govern the relationship that will exist between I and R as angles of incidence and refraction respectively. Now, we will not always have boundaries that are perpendicular to our wavefronts. Rather, we could also have a boundary in form of a lens. Now, how do we expect our wavefronts to behave when they come across such a boundary? Now, here we are going to have multiple change in media. We have the first one, which is air, and then we shall have our plane wavefronts. Let us call this lambda 1, which is the wavelength. The direction is from left to right. Now, when they come across the first phase of the boundary, we expect that they are going to bend so that we shall have something like this. And then we shall have a continuation in the direction of travel, again until we come to the second phase of the boundary, where further they are going to be bent so that they will now assume a circular shape. So as we continue, we shall have further bending so that now they will emerge as circular wavefronts. And this will continue until they converge at F, which is somewhere in front of our circular boundary. And then after F, they are going to diverge, maintaining the wavefronts. So here we shall have 4 media. This one is air. Now this one is the first phase. First phase, we shall have them bend a bit. Then we shall have them come to the second phase of our boundary, which is in form of a lens. Again, there will be further bending, and then we shall expect them to converge at a point F. They converge at F, and then they will spread from the same F, which is the focal point, and will continue diverging further. That is the much we can say about diffraction. Now, let us talk about yet another property of waves, which we are going to call diffraction. Now, we have looked at refraction. We have seen that refraction is actually that bending of waves when they come across an obstacle, and or when they change. We have seen that refraction is the bending at the interface of 2 media. We have looked at reflection. We said it's the bouncing back of waves when they come across a reflector. So now let us advance and talk about diffraction. Now let us advance and talk about diffraction and ask ourselves, what do we mean by diffraction of light? Diffraction of waves. And diffraction is the change in shape of wave fronts when they go round an obstacle or through a slit. That when waves go through an obstacle or they come across a slit, we are going to expect the wavefronts to change their shape, and that is the effect that we call diffraction. Take a look at this. Let us consider wavefronts which are plane, and we have some boundary here which has a slit. Now, this is the boundary and has a slit S1. Here, we have the spacing representing our wavelength. Now, what happens when these waves come across this boundary? They are going to change in shape, so that now we shall have emergent circular waves, emergent circular wavefronts. But what we need to note here is that the wavelength is not going to change. This time the wavelength is not going to change, so that now this will be the direction of the initial waves, and so will be the direction of the diffracted waves. These are the ones we call incident waves, and this one is the direction of diffracted waves. Diffracted waves. Now, the only aspect of these waves that is going to change is actually the shape of the wavefronts, but the wavelength, frequency, and speed are going to remain constant according to our relationship that we learned, according to the relationship that we learned. Now, there is one thing that we should note about diffraction. The extent will depend on the size of the slit. The extent will actually depend on the size of the slit. Take an example of wavefronts that go through an obstacle with a very big slit. Now, these wavefronts are going to emerge almost plane. They are actually going to emerge almost plane. So the change that we are looking for, is actually not to be going to be so much evident, because our aperture is actually very big in size. Now the wavelength is going to be maintained, the speed, the frequency, and all that. But again, the diffraction or the change of shape is not going to be all that clear. Now, if we consider the same wavefronts going through a very small slit, so that now we have the same plane waves, and we have a boundary with a very small slit here. With a very small slit, Now the change of shape is going to be quite clear, so that now we will have completely circular emergent waves. Completely circular emergent waves. The wavelength is still going to be maintained, and so will the speed and the frequency. Therefore, what we are saying, the smaller the slit, the greater the extent of diffraction. The smaller the extent of diffraction. The smaller the slit, the greater the extent of diffraction. You can consider another property we are going to call interference. Interference of waves. And interference of waves is basically merging of two waves. When two waves meet, we expect that they are going to merge and there will be some effect. Now, what we are supposed to note is that now their amplitude, or let us call it the amplitude of the resultant wave. The amplitude of resultant wave is going to be the vector sum. The vector sum of component amplitudes. That we have two waves with their distinct properties coming together, and we expect them to merge or combine. Now, depending on their individual characteristics, that is going to inform our resultant wave, and especially the amplitude. Note that we said a wave is actually a vector quantity. Therefore, the amplitude is a factor of direction as well as magnitude. Is a factor of magnitude as well as direction. Now, if so be the case, let us take an example of two waves. Example of two waves transverse in nature. Transverse in nature. That one is our first wave. Then probably we can have another one. We can have another one. Let us call that one wave 1. Then we have the second wave. Now, if this be a displacement time, if this be a displacement time plot, then we expect that the upper side of our y axis is positive. This one is positive and the other one is negative. Therefore, the amplitude of our first wave, let us call it positive A, while the amplitude of our second wave is going to be negative A. The frequency, the amplitude, the wavelength of these two waves is actually equal. However, because A is negative of the amplitude of our second wave by virtue of them traveling in different directions, then the amplitude of the resultant wave will be 0. The vector sum is going to give us 0. Therefore, what we are going to have is what we call the stationary wave. The resultant of the interference of the two is what we call the stationary wave. So if these ones, if 1 and 2 be the component waves, then the resultant wave, which we are going to call 3, will be a stationary. A stationary wave is one whose amplitude is actually 0. Because the two are merging, we add and we get the vector sum of the amplitude to be 0. Now, let us take examples of and see what would result from now for the condition for interference to occur, what conditions should we follow so that, or what should we observe in order for us to make sure that interference of our waves is actually successful? And we say that the sources of the waves should be coherent. The sources of our two waves should be coherent. In this way, we mean that the sources should be narrow, should be parallel, and should be close to each other. That the sources should be narrow, parallel, and close to each other. When the three are upheld, then we say that the sources in question are actually coherent. The sources are actually coherent. Now, depending on the individual properties of component waves, depending on individual properties of components, and by component waves we mean the two waves that are coming together to interfere, we could have the following results. The following results could be achieved. Now, before we even go to the results that we expect after interference, it is good that we ask ourselves, what properties are we talking about? What properties are these that we want to talk about? Number one, properties that we want to consider should be amplitude, should be direction of wave motion, and number three should be the speed of the waves. That we consider amplitude, direction, and speed of component waves, where component waves are the waves that are coming together in order for them to interfere to form the resultant wave. Now, the amplitude will inform the amplitude of the resultant waves, and that one is what we call the size of the resultant waves. Size of the resultant waves, which is going to be a vector sum of individual waves. Now, the direction will depend on the direction of the individual waves as well, and so will be the speed. However, the frequency is going to be maintained. The frequency of the component waves is going to be maintained, so that now the resultant wave is going to have the same frequency as that of the component waves. Now, here are the results. Number one, you could have a bigger wave, than the individual resultant wave could be bigger. It could also be smaller. You can have a smaller wave, or you could have no wave at all. You could have no wave at all. Now, let us consider each one of these individually and find out, when do we expect to have a bigger wave than the component waves? When do we expect to have a smaller wave than the component? Finally, when we expect to have no wave at all. Now, by so doing, we come to the types of interference. Types of interference. And A, we have what we call constructive interference. And when do we have constructive interference? It is when the resultant wave has a bigger amplitude than component waves. Where we have the resultant wave having a bigger amplitude. Now, this is what we mean. We said that amplitude of the resultant wave is actually a vector sum of the individual amplitudes. Therefore, let us take an example of two waves Let us take an example of two waves. One, we are going to give it amplitude 1. We are going to give it amplitude 1. Here's one. Then we have another wave. Another wave with amplitude 2. Let us call this one amplitude 2. And we bring them together so that they match. Now, what we expect is an even, no. In this case, the waves have amplitudes A1 and A2. We have amplitudes A1 and A2. Now, our waves have different amplitudes, and the vector sum will be A1 plus A2. Now, which means that our resultant wave will have an amplitude A3, which has an amplitude bigger than the components. So that now we shall have a bigger wave with a bigger amplitude. A3, which will be a component of the two individual amplitudes. So we shall have a bigger wave. That is a case of constructive interference. Constructive interference. Now, the other properties of the same would be varied or even would remain constant depending on other factors. Now, the other properties are the wavelength, the frequency, and the speed. Those are going to be informed by other factors, but of our interest here is the amplitude, which gives us the size. The amplitude gives us the size of a wave. The size of a wave. Now, that is constructive interference. Let us look at yet another type of interference, which we are going to call destructive interference. Destructive interference. And destructive interference is a situation where the amplitude of the resultant wave, is smaller than than individual amplitudes of component waves. That we want to make another wave, but we want it to have a smaller amplitude than the individual ones. That is when we shall expect to talk about destructive interference. Note that the size of a wave will always be given by the amplitude. Now let us take an example of such a wave. This one is actually a transverse wave. We call its amplitude A1. Then we can have a smaller wave. We can have a smaller wave. Smaller wave. With amplitude A2. In this case, we take direction into consideration and call it negative A2. Now, we will expect our resultant wave to have an amplitude equal to A1 plus negative A2, so that we have an amplitude A3 which is actually smaller than A1. And what we expect is that our new amplitude is going to take the direction of the bigger wave, so that now the resultant is going to be something like this. Which is going to be a wave having a smaller amplitude we are going to call A3, and in the direction of the bigger wave. In the direction of the bigger wave. However, from the series of crests and troughs that we have, you can be able to observe that actually we are maintaining the frequency. We are maintaining the frequency, so that frequency F1 will be equal to F2, will be equal to F3, where frequency F1 is that of wave 1, frequency F2 is that of the second wave, and the third frequency will be that of our resultant wave. Will be that of our resultant wave. Then we can talk about the last type of interference, which we are going to call total destructive interference. Total destructive interference. And total destructive interference is a component. It is a component of equal waves that are out of phase. Out of phase. Now, by equal waves, we talk about equal frequency, equal amplitude, equal speed, But now the only aspect that is actually different here is the direction. Different direction. Therefore, for total destructive interference to take place, you expect that the waves that are involved should have the same frequency, the same amplitude, the same speed, but they should only differ in their direction of travel. Now, let us draw this situation. We can draw the situation so that we have the component waves being equal but are out of phase. Are out of phase. They are actually out of phase. We call this one amplitude A. The amplitude of our second wave should be negative A. Now again we said that the amplitude of the resultant wave is actually the vector sum of individual amplitudes. Therefore, our resultant wave is going to have an amplitude equal to this, which will give us 0. And that way, we will have no wave at all. Therefore, we shall have a resultant wave being a wave with no amplitude at all. This is the resultant wave, which has 0 amplitude. It's actually 0 amplitude. That way we have total destructive interference having taken place. So that now the last wave we are going to generate is going to have 0 amplitude. 0 amplitude. Therefore, what we mean is that we have conditions where interference will take place. Number one is that the waves must be of same type. For example, you cannot talk about interference of a longitudinal and a transverse wave. They have to be both longitudinal or transverse for us to have some results. Then we are saying that the sources of the waves have to be coherent. They have to be coherent, and by that we mean they should be small or even narrow. In case of a slit, then they should be parallel, and then they should be narrow, parallel, and close to each other. They should be narrow, parallel, and close to each other. Now we are going to look at two situations. Two situations in our daily lives where we shall look at interference of light and interference of sound waves, so that we can explain why things happen around us the way they do. But that should be in our next lesson. Thank you.